Today, I, as a layman person, am going to read a physics research paper, the entire 12 pages. I am currently on arxiv archive.org, and I put in the search bar quantum gravity. I got 42,000 results, and I just scrolled through a few of them. I wanted to make sure that I wasn't going to be reading too many pages and that there was going to be some tables and figures. That means more pictures, and I really want to see if I, as a layman person, can understand what this paper is trying to say and what current research is up to these days. The paper that I chose to read, the 6th result, I didn't want to scroll through all of them. This one sounded cool. It said polymer black hole surrounded by quintessence. I don't know what a polymer black hole means, and I don't know what quintessence means, but it sounds really interesting, and maybe they will tell us what that's all about, like, define that shit so I understand it. I don't want to have to look it up. This paper was published July 9th, 2025. It's got 12 pages, 10 figures, and 1 table. So let's get right on into it, see what we learn. And a quick shout out to the authors of this paper. In this paper, we study the polymer black hole solution surrounded by a quintessence field. The influence of quintessence on the polymer black hole is investigated through its thermodynamic properties, such as the Hawking temperature, entropy, and specific heat, which allows us to address the question of thermodynamic stability. We then calculate bounds on the electromagnetic gray body factors and photon emission rates of the black hole, highlighting the interplay between quintessence and quantum gravity effects in determining these phenomena. We also examine the effects of quintessence and quantum gravity on the geodesics and shadows of massless particles around the black hole. Our results are further compared with observational data of the Sagittarius A black hole from the Event Horizon Telescope. Wow. I have no idea what I just read. I don't think I retained any of that. I might have to reread it. Okay, so there is something called quintessence that is influencing this polymer black hole through heat, which allows us to address the question of thermodynamic stability, like thermal equilibrium, I believe we're talking about here. Yes, of course. We then calculate bounds on the electromagnetic gray body factors and photon emission rates of the black hole. I don't know what gray body factors is. It sounds like some, I don't know why I keep thinking alien, like, oh, gray alien, gray body of the alien. So it's an electromagnetic alien, and there's light coming from the black hole. Okay, cool. Highlighting the interplay between quintessence and quantum gravity effects in determining these phenomena. Nice. So there's quintessence and quantum gravity around this black hole. We also examine the effects of quintessence and quantum gravity on the geodesics and shadows of massless particles around the black hole. So light, when traveling as photons, will follow its geodesics, the world line of the fabric of space-time. And when mass curves that shit, light follows that shit. Shadows of massless particles. That sounds very weird. Shadows of massless particles. How do you have a shadow of light? I'm just so confused here now. Anyways, introduction. As is well known, the solutions to Einstein's field equations and general relativity are plagued by the presence of undesirable singularities. These singularities mark the breakdown of the theory, indicating the limits of its applicability when quantum gravity effects become significant, typically when the curvature reaches the Planck scale. The actual existence of singularities in nature is generally questioned, and it is widely believed that a complete theory of quantum gravity would be able to resolve them. replacing the singular behavior with some form of regular phenomena. In this context, numerous approaches to quantum gravity have been proposed, among which we highlight loop quantum gravity, string theory, ADS-CFT correspondence, and the frameworks involving non-commutative geometry. Oh man, this is like a lot. So, at the beginning of the universe, we have a singularity at the Big Bang, and then in black holes, we also have singularities, especially when quantum gravitational effects become significant, typically when the curvature reaches the Planck scale. So that's like the smallest known form of scale. And it is widely believed that a complete theory of quantum gravity would be able to resolve them, replacing the singular behavior with some form of regular phenomena. So we should, with quantum gravity, be able to understand why this is happening, why we get these singularities. So then it says, here's what we've proposed so far as a community. Yeah, okay. So I think that made sense. Although a complete quantum theory of quantum gravity has not yet been achieved, the development of numerous effective models has been served as an important testing ground for addressing such classical issues. Within the context of loop quantum gravity, for instance, the successful Friedmann FLRW cosmological models have been proposed. These models describe a homogeneous and isotropic universe on large scales. So, generally, it's the same everywhere, and naturally resolve the singularity problem by introducing an effective space-time in which the traditional Big Bang is replaced by a Big Bounce scenario. Okay, so loop quantum gravity does not say Big Bang, it says Big Bounce. It is important to note that these effective models rely on the regularization of phase space through a procedure known as polymerization. Recently, a quantum extension of the Schwarzschild black hole based on the polymer quantization approach of LQG was proposed. In this framework, the effective quantum spacetime gives rise to what is referred to as a polymer black hole, in which the classical singularity is replaced by a quantum bounce, connecting a black hole region to a white hole region. The rotating counterpart of the polymeric Schwarzschild black hole has also been investigated in reference. It is worth mentioning that black holes inspired by LQG have been tested against observations from the Event Horizon Telescope collaborations, with their parameters constrained by experimental data from the supermassive black holes M87 and Sagittarius A star. Additional phenomenological studies involving black hole observations and gravitational waves can be found in references. Okay, so in loop quantum gravity, there is a bouncing singularity that is not a Big Bang, but it's a continuous expansion and contraction connecting a black hole region to a white hole region. So are both the black hole region and white hole region bouncing? And do they have their own bounces, or is it connected into one collective bounce for both regions? Okay, in this paper we analyzed the polymer black hole surrounded by quintessence associated with negative pressure states that drive the accelerated expansion of the universe. Quintessence emerges as an alternative proposal to dark energy, in contrast to the cosmological constant model. So it's dark energy, but it's not the cosmological constant model. The latter implies an energy scale vastly larger than the one referred to from observations of dark energy. In general, quintessence is described by a canonical scalar field minimally coupled to gravity, and it represents the simplest scenario capable of avoiding theoretical issues such as ghost and Laplacian instabilities. Here the influence of quintessence on the polymer black hole will first be investigated in the context of black hole thermodynamics. Specifically, we focus on computing the Hawking temperature, entropy, and associated heat capacity in order to address questions related to thermodynamic stability. Subsequently, we will examine the effect of quintessence on geodesics and shadows of massive particles around the black hole. Related studies along similar lines can be found. So, a polymer black hole is surrounded by this quintessence, which has negative energy and drives the accelerated expansion of the universe. They're going to use heat around the black hole to investigate this. Quintessence has an effect on the geodesics of spacetime and shadows of massless particles around the black hole. That shadow part is really tripping me out. Like, I'm really intrigued to know what this means. This paper is organized as follows. In the next section, we present a brief review about the polymer black hole, discussing the main aspects about the event horizon and such model. Okay, so it just goes into how it's organized. Cool. In this section, we briefly discuss some of the features of a polymer black hole, which arises within the framework of loop quantum gravity under the condition. Look at all of this math. Bruh. I'm not going to be able to understand these symbols. So it's been about a week, 8 days to be precise. I guess the first page really took a toll on me. I don't know. But we're back, and all I remember is talked about quintessence and polymer black holes, and then we got into some math, and yeah, so let's continue on with the rest of the paper. This solution, which represents a quantum extension of the Schwarzschild metric in LQG, is characterized by the coefficients, where MB and MW are direct observables representing conserved quantities in the model, and here, tent is a quantum parameter associated with holonomy modifications in LQG. As a remarkable feature, it is worth highlighting that the singularity typically associated with a polymer black hole can be replaced by a space-like transition surface that smoothly connects an asymptotically Schwarzschild black hole to a white hole, with MB and MW denoting their respective masses. This transition occurs when the coefficient BR reaches its minimum at R equals 0, thus recalling the quantum bounce scenario of the loop quantum cosmology. Now considering a symmetric bounce structure, we can set with playing the role of the metric lapse function. Note that under this assumption, AR and BR take on the simplified forms, respectively. In figure 1, we have plotted the lapse function as a function of the radial coordinate r for several values of tent, from which we can conclude that the metric defined by the line element leads to a single event horizon. Since the cosmological horizon is absent in the model, as AR goes to infinity equals 1, the expression for the event horizon can be written as, and the necessary condition for its existence, note that when tent equals 0, the Schwarzschild radius is recovered as expected from the structure of the interval in EQ, whatever that means, 5. Figure 1 also indicates that the polymer black hole is a regular object, as no singularity is observed at any finite value of r. This indication can be further confirmed by examining Kretschmann scalar. So I can't really say what any of that means, but it sounds like they are using this math to represent this polymer black hole within the framework of loop quantum gravity to explain this bouncing mechanism using this wonderful math. In particular, we will be concerned with this symmetric bounce structure, albeit in the context of a black hole surrounded by quintessence, as we shall implement the next section. Okay, so on page 3 we have figure 1, which says the lapse function plotted against the radial coordinate r for several values of tent. We have assumed m equals 1 for this plot. Okay, so it looks like when r increases, or when the lapse function times the radial coordinate increases, r, the radial coordinate, will also increase, but it hits this plateau where it kind of just levels out when it reaches 1, when tent reaches 1. Whatever this means, nice. Quintessence effects part 3. According to Kiselev, in a static and spherically symmetric configuration, the quintessence field surrounding a black hole must satisfy this condition. It denotes components of energy momentum tensor associated with the field, and W is its equation of state parameter, which must satisfy this condition in order to remain consistent with astronomical observations of an accelerating universe. It is important to note that when W equals -1, the scenario reduces to that of a cosmological constant, where as W equals -1/3 corresponds to a universe undergoing uniform expansion. In this work, we aim to investigate a combined framework involving a polymer black hole surrounded by a quintessence field. Following Kiselev's approach, the effects of quintessence can be incorporated through a redefinition of the lapse function of the metric, achieved by adding a term proportional to r. Our starting point, therefore, will be a line element of the form given in EQ5, with a modified lapse function defined by this thing, where C is a constant parameter that effectively describes a coupling of the quintessence matter with the polymer black hole system. The behavior of EQ as a function of the radial coordinate r is illustrated in figure 2. It is evident that a direct consequence of the quintessence effect is the emergence of a new event horizon, the cosmological horizon, which was absent in the case of the pure polymer black hole, as previously discussed in the preceding section. So they're saying that with a normal polymer black hole, the cosmological horizon is absent. But when you add this quintessence effect, a new horizon emerges. I hope I'm getting that correctly. From the upper left panel of the same figure, we can observe that the increasing value of the parameter C shifts the event horizon further to the right, while simultaneously shifting the cosmological horizon further to the left. Okay, so the event horizon of the black hole is on the right hand side, and the cosmological horizon is on the left hand side of these lines. It is worth noting that the effect on the cosmological horizon is more pronounced than on the event horizon. It seems like on the left hand side, the cosmological horizon, when C gets closer to 0, will bunch up together. Then C is a constant parameter that effectively describes a coupling of the quintessence matter with the polymer black hole system. Okay, so this is with quintessence, this dark energy thing, and this polymer black hole. When it's coupled, it's C, and when it reaches 0, the cosmological horizon bunches up like this. And on the right hand side, we get the regular horizon of the black hole, which seems to spread out. Okay, that is my mistake. When C is at -1, then we get the infinities of the cosmological horizon. That's why it's like so tightly packed together. But then when C reaches 0, then the event horizon of the black hole spread out. Moreover, the condition for black hole formation, that is, the existence of a horizon, may no longer be satisfied if the value of C exceeds a certain threshold, depending on the specific choice of parameters. So when C reaches 0, then the black hole doesn't form? I'm confused now. But the cosmological horizon is formed, and an opposite behavior is observed in the case of the upper right panel, where the event horizon appears to shift to the left as the cosmological horizon shifts to the right for increasing values of this symbol, which I still don't know what this means. Furthermore, the impact on the former seems to be more pronounced than on the latter. It is also worth noting that the curve intersects the vertical axis at increasingly higher values as tent grows. This suggests that for sufficiently large values of tent, the event horizon radius ceases to exist. More precisely, it is effectively replaced by a horizon of purely cosmological nature. Oh man, so it's flipped. So the cosmological horizon is not as pronounced as the one for this black hole on the right hand side, because now the black hole has all bunched up lines and it's like an infinity. But then on the left hand side, the cosmological horizons all spread out. I'm getting really confused. For sufficiently large values of this parameter, the event horizon radius ceases to exist. More precisely, it is effectively replaced by a horizon of purely cosmological nature. Oh. So is it saying that this is like the flipping, the bounce into the white hole? However, this scenario never actually occurs, since this condition must be satisfied. In the lower panel of the figure, we observe a behavior similar to that shown in the upper left panel, where the event horizon appears to shift to the right while the cosmological horizon shifts to the left. It is also worth noting that the latter seems to be significantly affected by the values of W becoming increasingly closer to the former as W decreases. The figure further suggests that the condition for the existence of a black hole, i.e. the existence of a horizon, might eventually be violated, since the maximum of the plotted function decreases in magnitude as W is reduced. However, this does not actually occur due to the lower bound imposed on W, at least for the fixed parameter values considered in the figure. It is also worth noting that the presence of quintessence appears to render the solution non-regular in the limit as R reaches infinity, as well as the origin, since this behavior is confirmed by the Kretschmann scalar, which in this limit R reaches 0 takes the form. Okay, so by looking at this third figure, it's basically the same thing as the top left figure, where the cosmological constant moves to the left and the event horizon of the black hole moves to the right, and when W decreases, that means that the black hole basically won't form at all. So when the plot hits 0, it's basically infinity, right? As we can see, the solution becomes regular when there is no quintessence, i.e. for C equals 0. So when C equals 0, there is no dark energy around this black hole. If there's no dark energy around this black hole, then there's no black hole. And that's what they say. But when there is quintessence around the black hole, then it goes into this, it flips. It does the bounce. The full expression of the Kretschmann scalar is excessively long, and for the sake of clarity and consciences will not be included here. What? I thought that was the scalar model. That's not even the full thing. Jesus. So these two panels, basically when C increases, then the temperature of the black hole will decrease, and that there is negative energy around the black hole that counteracts gravity, effectively lowering the surface gravity at the event horizon and thus resulting in a cooler black hole. So they're making black holes colder by increasing these parameters of quintessence and polymerization. On the other hand, the polymer parameter quantifies quantum corrections from LQG that introduce a quantum repulsion which smears out the spacetime curvature. This also leads to a reduced surface gravity and consequently a lower Hawking radiation. Therefore, both phenomena, one classical and one cosmological, and the other quantum gravitational, contribute to increasing the black hole's thermodynamic stability by slowing its evaporation rate. However, a more suitable and fundamental divergence is revealed in how C and tent influence the characteristic scale, i.e. the event horizon radius at which this peak temperature is achieved. An increase in C shifts the temperature peak to smaller horizon radii, suggesting that in a quintessence-dominated scenario, the black hole reaches its hottest emission phase when it is comparatively smaller. So when the black hole is smaller, it's hotter. In contrast, an increase in tent shifts the peak temperature to larger horizon radii. This indicates the quantum effects become thermally dominant at a larger scale, pushing the peak emission outwards. Such a competition of scales implies that the final thermodynamics and life cycle of such a black hole would depend on the relative strength between the influence of surrounding dark energy and the intrinsic quantum gravitational modifications to spacetime. Oh man. Okay, so when the black hole is smaller in a quintessence dominant scenario, it is hotter. In contrast, quantum effects become thermally dominant at a larger scale. So when the black hole is bigger, the quantum gravitational effects around the black hole become more prominent, and so it also becomes hotter. And so this is the competition of scales that the thermodynamics and life cycle of such a black hole would depend on. Figure 4 presents the entropy as a function of the event horizon radius following the prescription. In general, one can observe that the entropy increases as either the quintessence coupling parameter C or the polymerization parameter tent increases. Furthermore, it is evident from the left panel of the figure that entropy is not well defined for all values of RH. In fact, the maximum value of the event horizon radius for which the entropy remains well behaved decreases as C increases. A similar behavior is also observed in the configuration shown in the right panel, although it is not immediately evident due to the way the results were presented for clarity. There, the limiting values of RH for which the entropy is well defined are very close to one another, indicating that they are only slightly affected by variations in tent. With the entropy at hand, we can directly compute the heat capacity C. The results are shown in Figure 5. The heat capacity is a fundamental thermodynamic quantity that provides insights into the local stability of the system, as it reflects how the black hole responds to small temperature perturbations, as shown in both the left and right panels of Figure 5. One can identify stable states, characterized by positive values of C, and unstable states, negative values of C, associated with second-order phase transitions marked by discontinuities in the maximum value of the Hawking temperature. Furthermore, for both the stable and unstable configurations in the left panel, the heat capacity appears to increase as the parameter C increases, and opposite behavior is observed in the right panel, where the entropy is higher for smaller values of tent in both configurations of the system. Oh man, that's going to take a lot to try to understand. Okay, so when the event horizon radius increases, then the entropy increases. And as the entropy increases, that means that the quintessence coupling parameter or the polymerization parameter also increases. So as the black hole becomes more polymerized, it increases in temperature, nice, and thus entropy, as well as when there is more quintessence around the black hole, it also increases in temperature or entropy. Cool. Part 5. Bounds in the electromagnetic gray body factor and particle emission rate. In this section, we calculate the gray body factor lower bounds associated with the transmission of outgoing photons through the effective potential barrier surrounding the black hole. These bounds can also be expressed in terms of Bogoliubov coefficients. Such results may be considered as general bounds on these coefficients. Due to their generality, they serve as powerful tools for gaining qualitative insight into one-dimensional scattering phenomena. Moreover, this approach provides a unifying framework that connects a variety of seemingly unrelated results derived in specific cases. For more details, see references. The radial equation for the electromagnetic field can be written in terms of a Schrödinger-like equation for introducing tortoise coordinates leading to this, where W is the frequency identified with the particle energy. The tortoise coordinate is defined from this thing, and the effective potential is written as, see the reference. Here we consider the model F equals 1, or L, is that an F? The lower bound for the gray body factor identified with the transmission coefficient through the potential barrier, which quantifies the deviation of a black hole's radiation from that of an ideal black body, is given by see references, and the particle emission rate, which is the number of particles per time unit per frequency unit, where T is the absolute temperature. That, in our case, coincides with the Hawking one. Considering the electromagnetic effective potential in EQ, as well as the expressions, we arrive at the analysis of the lower bound for the photon emission rate, depicted in Figure 6 as a function of particle energy W, reveals the distinct thermodynamic impact of quintessence and polymer parameters. The upper panels demonstrate a clear trend, an increase in either the quintessence coupling C or the polymer parameter, which leads to a significant suppression of the emission rate across the entire energy spectrum. This result is a direct consequence of the black hole's modified thermodynamics. As established in the analysis of the Hawking temperature, both a stronger quintessence field and more pronounced polymer corrections act to tool the black hole. According to the particle emission formula, a lower temperature, Th, increases the magnitude of the thermal term in the denominator, thereby reducing the number of emitted particles per unit time. This confirms that both quintessence and quantum gravity effects make the black hole a less efficient thermal radiator. Holy fucking dog shit. So when C is at its lowest, then there's more photon emission. Likewise, when tent is at its lowest, the photon emission rate is at its highest. So when tent or C increases, so this is quintessence or polymerization, when they increase, the photon emission rate is less. I would think that it would be the other way around, right? Furthermore, the lower panel of Figure 6 illustrates the influence of the black hole's size on the emission rate by varying the event horizon radius RH. The graph shows that as this latter increases, the peak emission rate diminishes drastically, and the entire emission spectrum shifts toward lower particle energies, W. This behavior is characteristic of thermal radiation from black bodies, where larger and typically cooler objects radiate less intensely and have their emission peak at lower frequencies. For the given set of parameters, a larger black hole is thermodynamically cooler, which explains both the overall reduction in luminosity and the redshift of its peak energy output. This underscores that the horizon size is a dominant factor in governing the black hole's radiative properties, with larger black holes being significantly dimmer and emitting lower energy photons. So as RH, which is the event horizon, increases, so as the black hole gets bigger, then the emission rate will be less and less, and that would imply lower energy particles, making the black hole smaller, or making the black hole cooler. Okay, I actually think I understand this bottom table here. Part 6, Geodesics and Shadows. In this section, we will analyze the geodesic motion of light-like test particles around the polymer black hole surrounded by quintessence. Since our metric depends only on the radial coordinate r, two killing vectors associated with conserved quantities can be identified. The first one, related to time translation symmetry, leads to a conserved energy expression of this thing, where the dot denotes differentiation with respect to the affine parameter. The second vector, k, u, leads to the conservation of angular momentum. In this analysis, we restrict ourselves to the equatorial plane, which corresponds to 0 equals pi divided by 2, a simplification allowed by the spherical symmetry of the system. Under this condition, the metric given in EQ5 can be simplified in the form: the Lagrangian function associated with the above metric takes form, which can be further rearranged in terms of the derivative of the radial coordinate with respect to the affine parameter, as here represents the norm of the tangent vector along the geodesic path and takes the value 0 for the light-like geodesics of interest. Thus we can write represents the effective potential for the polymer black hole surrounded by quintessence. We finally get the following equation for node, where that thing defines the impact parameter. In figures 7 and 8, we've depicted the ray tracing for light particles around the polymer black hole under the influence of quintessence. For both plots, we have considered m equals 1. In figure 7, we aim to investigate the influence of the w parameter in the light trajectories. For this purpose, we have set c equals. Here, we choose to work with a tent rather than a tent. Given that m equals 1, and vary the w parameter by choosing that thing, as we can be clearly seen from the figure, decreasing the value of w toward w equals minus 1. I feel stupid just reading these fucking numbers, but I feel like I have to. That's like in certain cases. Causes the black hole horizon radius to increase, and light particles tend to become more confined. It is important to highlight that for all plots we have considered the same impact parameter as well. In figure 8, we focus on examining the geodesics of light trajectories around a polymer black hole surrounded by a quintessence field for a fixed value of w, namely w equals -1/2, while varying the loop quantum gravity parameter a tenth and the quintessence parameter c. In this figure, we have constructed a panel in which the rows have a fixed value for a tenth, or the columns have a fixed value for c. We have considered four values of c, namely c, 0.5, 0.10, 0.15, and 0.20. Similarly, we have considered 4 values for a tenth equals 0.2, 0.3, 0.4, 0.5. Notice that for any value of a tenth, if we increase the value of c parameter, the black hole becomes larger, i.e. increasing of c promotes an increasing of the horizon radius, and therefore the net effect on the light trajectory is a great tendency to confinement. On the other hand, if we consider any value of c, the increasing in the a tenth parameter promotes a decreasing in the size of the black hole, smaller horizon radius, which leads to a smaller tendency to confinement of the light particles around the black hole. The values of the horizon radius are h, the photon ring radius, p, r, and the shadow radius, sh, for the configurations according to the panel figure 8 can be consulted in Table 1. In Figure 9, we have depicted the shadows of 3 configurations of the parameters. For the plots, we have considered w blah 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 and 3 values of a tenth, namely blah 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 blah. The green dashed line was included in the figure for the sake of comparison so that it becomes easier to see that the radius of the shadow indeed becomes smaller as we increase the value of a. We also compare our shadow results with the observational data of the Sagittarius A black hole according to the Keck data from the east. Oh man. In Figure 10, we compared the values of the shadow radius for the polymer black hole surrounded by quintessence with the range of the shadow. Fuck. Okay, so that last clip was 6 days ago. So it's now taking me over 3 weeks to read this 12-page paper. Now, last time I was kind of fucked up, and so I had to stop. I couldn't take it anymore. This week, bruh, I got like one more page, a page and a half, and then we get references. So, if I do not finish this video in this moment, bruh, this shit will never come out. And it's probably for the best, honestly. It's quite embarrassing to, try to read in front of you. But fuck it, this is where I am at the moment. And I don't remember anything from last week. Fuck. In figure 10, we compared the values of the shadow radius for the polymer black hole surrounded by quintessence with the range of the shadow of Sagittarius A star, expressed in EQ29. We considered 3 values of A, each one for each graph in figure 10. We also considered 3 values of W, namely -1/2, -2/3, and -4/5. In each graph in figure 10, we varied C in a range from 0.05 to 0.2. It becomes clear that there is a wide range of values for C in combination with A and W, such that the shadow radius for the polymer black hole surrounded by quintessence matches the range of the image from A star. It is important to highlight that the shape and size of the shadow boundary have a very weak dependence on black hole spin and the observer's inclination. Hence, our considerations of axial shadows analysis and the fact that our black hole model has no angular momentum are in agreement with the EHT data consideration. The fuck does that all mean, bro? Part 7, Final Remarks. In this paper, we have investigated the polymer black hole surrounded by quintessence in different contexts, such as black hole thermodynamics and the geodesics and shadows of massless particles. Our analysis in section... I don't know what... I can't read Roman numerals if it's not in chronological order. Is that 4? Reveals an intriguing interplay between cosmological and quantum gravitational effects. An increased influence of dark energy modeled by the quintessence field and parameterized by the constant C. We have used the state parameter W equals -2/3, which leads to a decrease in the Hawking temperature, with the thermal peak occurring for smaller black holes. In contrast, a stronger presence of quantum gravity corrections governed by the polymerization parameter also results in lower temperatures, but with the thermal peak shifting towards larger black hole sizes. This contrasting behavior illustrates how each physical contribution, cosmological in the case of quintessence and quantum in the case of the polymer effects, modulates the black hole's thermodynamic behavior in distinct ways, ultimately shaping its evaporation process and thermal evolution. In the same section, we carried out an analysis of the entropy and the associated heat capacity, where we found that the entropy is not well defined for all values of the horizon radius. In fact, the maximum value of the radius, for which the entropy remains well defined, decreases as both the cosmological parameter C and the quantum parameter tend to increase. Moreover, the entropy tends to take increasingly larger values of C and tent. Regarding the heat capacity, our results indicate the presence of both stable and unstable states, associated with second-order phase transitions occurring at the maximum value of the Hawking temperature. For both stable and unstable configurations, The heat capacity was found to increase with increasing values of C. In contrast, an opposite behavior was observed with respect to the parameter, where smaller values of it lead to a larger heat capacity. Following, we investigated the lower bounds for the gray body factors of the electromagnetic radiation and the associated particle emission rate. We observed that both the parameters C and 10 act synergistically to suppress the particle emission spectrum, which is consistent with the previously discussed reduction in Hawking temperature. The overall decrease in the emission rate across the energy spectrum, along with the shift of the peak to lower frequencies as the event horizon radius increases, reflects the typical behavior of larger and cooler black bodies. These findings reinforce the notion that the polymeric black hole surrounded by quintessence behaves as a less efficient thermal radiator with a significantly redshifted emission spectrum, an effect that may have important implications for the observational signatures of such objects. The analysis developed in section 6 investigates how the LQG parameter and the quintessence parameters influence geodesics of light-like particles and the black hole shadow. We could see that for fixed C and A, by decreasing the value of W approaching -1, the black hole horizon radius becomes bigger and the light particles tend to become more confined. In order to investigate the role played by C and A parameter in the light-like particles geodesics, we have set W to -1/2 and varied C and A. We could notice that for any value of A, if we increase the value of the C parameter, the black hole becomes larger. The increasing of C promotes an increasing of the horizon radius, and therefore the net effect of the light trajectory is a greater tendency to confinement. On the other hand, if we consider any value of C, the increasing in the A parameter promotes a decreasing in the size of the black hole, which leads to a smaller tendency to confinement of the light particles around the black hole. Also, the shadows were computed for several configurations, and we could find a wide range of configurations of A, C, and W, in which the shadow size matches the data of the Sagittarius A black hole. Acknowledgements. Holy shit. So we are finally done with this paper. I just have two questions, really, and that is, what does shadows of massless particles mean, and what does gray body factors mean? Now, they might not be the most important aspect of this paper, but these are the two lingering questions that I have on my mind, and so I'm going to ask ChatGPT. So, gray body factors are a measure of how much the radiation emitted by a black hole deviates from a perfect black body spectrum. A perfect black body absorbs all radiation that falls on it, and emits radiation with a spectrum that depends only on its temperature. Stephen Hawking predicted that black holes emit thermal radiation, as if they were black bodies. However, this radiation, when it travels away from the black hole, encounters the black hole's own gravitational potential. This gravitational field acts as a potential barrier, reflecting some of the radiation back into the black hole and allowing only a fraction to escape to a distant observer. Because not all the radiation escapes, the black hole doesn't behave like a perfect black body from the perspective of a distant observer. Instead, it's a gray body. The gray body factor quantifies this transmission probability, how much of the Hawking radiation successfully escapes the black hole's gravitational pull. The shadow of a black hole is the dark region that appears against a bright background of light, caused by the strong gravitational lensing of light around the object. When light rays pass very close to a black hole, they can either be captured by the black hole's event horizon or deflected and escape. There is a critical impact parameter, a specific distance from the black hole center at which photons can orbit the black hole in unstable, nearly circular paths, forming what is called a photon sphere or photon orbit. Light rays that originate from behind this photon sphere and are on paths that would eventually fall into the black hole never reach a distant observer. This creates the shadow, a dark silhouette in the sky. Man, I might need to see a picture. So I have rediscovered being an idiot. This happens almost daily. And after looking at a picture of a black hole, the shadow aspect of it is the dark region at the center where it looks black. So that kind of makes some sense now. But there's this lensing effect that distant observers see, which makes that shit look dark as fuck. The concept of the shadow is primarily discussed in the context of massless particles like photons, because their trajectories are null geodesics, meaning they follow paths dictated solely by spacetime curvature. While the concept has been extended to massive particle surfaces, for massive particles, direct observational shadow we see is due to light. Okay, so in summary, this paper talked about quintessence, which is this dark energy thing that's not dark energy, it's like a different type of dark energy, and a polymer black hole, which is from loop quantum gravity, and there's this like bouncing effect, and we learned a little bit about gray body factors, and we also learned a little bit about understanding the shadows of massless particles. And I'm not really sure if I really retained much of what this paper was trying to talk about. That's okay. I feel like I've learned a little bit though, and even though I struggled reading this paper, it took me 3 goddamn fucking weeks. I had a good time trying to wrap my head around what these figures were, describing, and it was a good time, and I hope that you also had a good time. This video is going to be super long, so if you stuck out to the very end, holy crap, honestly, kudos to you, because I don't think I will even watch this video over again. I'm going to edit it, and that's it. This video is done, and goodbye.